Hello everyone. Today I will be presenting a paper review of BEVFusion, a multi-sensor fusion framework published at ICRA 2023. This paper was written by Zijian Liu, Huanten Tang, and their collaborator at MIT. It addressed a fundamental question in autonomous driving perception. How do you effectively combine data from camera and LiDAR sensor? The paper proposed a new approach called BEVFusion that unifies sensor data in shared bird-eye view representation space. Let me talk through why this matters, how it works, and what I think about this. Here is the outline of my presentation. I will cover 6 sessions. First, the motivation. Why does this paper exist and what problem it's solving? Second, the main contribution of the paper. Third, the core technical method, the architecture, and the key engineering optimization. Fourth, the experimental result on major benchmark. Fifth, the limitation I identify in this work. And sixth, my own critical analysis and an improvement idea I'm proposing. Let's start with the motivation. So why does this paper exist? Let us start with the basic. Modern self-driving vehicles use multiple sensors. For example, human vehicles have 29 cameras, 6 radar, and 5 LiDAR. Each sensor provides something the other cannot. Camera give you semantic information. You can identify color, texture, traffic sign, line marking. LiDAR give you precision 3D geometry, accurate depth, and spatial structure. Radar give you velocity estimation and work well in bad weather. The problem is that these sensors see the world in completely different format. Camera produce 2D perspective image, LiDAR produce 3D point cloud. They are fundamentally different data representation. So the big question this paper tells is how do you combine or fuse these different data without losing important information for the one. And as we will see on the next slide, prior approach all had this problem of losing information during the fusion process. Before BEVFusion, there were 2 main approaches to sensor fusion, and both had serious flaws. Approach A was to project LiDAR data onto the camera view, basically creating an LGBT image. The problem is this geometrically lossy. 2 points that are far apart in the 3D space can end up as neighbor in the 2D camera projection. So you lose the spatial structure that LiDAR provides. The approach B, which was more popular, was the opposite direction. Methods like point painting, MVP, and deep fusion will take camera feature and paint them into LiDAR point. But this is semantically lossy. A typical 32 band LiDAR only capture about 5% of the scene that camera see. So 95% of the rich camera information just get thrown away because of there is no match LiDAR point. BEVFusion take a completely different approach. Instead of forcing one sensor into other space, it transforms both into a shared bird-eye view, like looking down from above. This BEV space preserves the geometry structure from LiDAR and the semantic density from the camera. Neither modality loses information. Now let me summarize the four main contributions of this paper. First, the unified BEV representation. Both camera and LiDAR feature are converted into the same BEV view space. This is the core conceptual contribution. Nobody loses information. Second, and this is the major engineering contribution, they develop an efficient BEV pooling operation that achieve a 40 time speed up. The camera to BEV transformation was extremely slow, over 500 milliseconds, which made the whole approach impractical. They brought it down just to 20 millisec 12 milliseconds usage. Too technical, I will explain shortly. That the architecture is task diagnostic. The same fuse BEV feature can be used for 3D object detection and BEV map segmentation just by swapping the task specific heads. So you don't need to redesign the model for different tasks. Fourth, the result, BEVFusion set new state of the art on the BEV Nucin and YEMO benchmark with 1.3% higher detection accuracy and a massive 30.6% improvement on the map segmentation. And it does this for almost half of computation cost of prior method. Now let me go through the architecture pipeline from left to right. We start with the sensor input, see multi-viewer camera and LiDAR point cloud. These go through separate modality specific encoder. The camera image are processed by a swing transformer backbone with a future parameter pyramid network. The LiDAR point cloud go through VosNet, which fossilize the point and extract future using sparse convolution. The critical step in the BEV transformation in the middle. For LiDAR, this is straightforward. You just flatten the 3D vowel future along the head axis to get a top-down BEV map. For camera, it is much harder because you need to figure out the depth. I will explain this in detail in the next slide. This is the most technically important part of the paper, so let me explain it carefully. Converting camera feature to BEV is not straightforward because camera image do not contain depth information. The camera see the world in perspective. You know the decision of each pixel, but not how far things are. Step 1. Following the LLS method by Fillion and Fielder, they predict a discrete depth distribution for each camera pixel. So instead of saying this pixel is at 10 meter, the model say it is a 30% chance is it at 10 meter, 50% chance at 15 meter, and so on. Each pixel is then scattered into D discrete point along its camera ray with future scaled by those depth probability. Step 2, this creates a massive 3D future point cloud with C camera each with a 32 by 88 future map and 18 depth bins. You get about 2 million points per frame. That is 2 order of magnitude denser than a typical LiDAR point cloud. The step 3, these 2 million points are then quantized into BEV grades. For example, with a 0.4 meter resolution and all the features within each grid cell are pulled together. Here is the problem. This pull operation was extremely slow. In the original LSS implementation, it took over 500 milliseconds on an RTI ternary GPU. That is over 80% of the model total runtime. This made the whole approach impractical for real-time driving. So this slide show the two optimization. The first optimization is pre-computation and the second is interval reduction. So let us look at the 3D object detection result on the NUC benchmark. This tab shows the comparison. The metric are MAP, mean average precision, and NGP, nuisance detection score. Higher is better for both. Now this is where BEVFusion really demonstrates its advantage. Map segmentation is about identifying driver area, crosswalk, walkaway, parking area, and lane divider from a top-down view. This is semantic task, not a geometric one. Look at the result. The camera-only BEV Fusion model achieved 56.6, which actually better than the LiDAR-only center point at 48.6. This is exactly the opposite of what we saw in the detection where LiDAR dominates. It makes sense. Cameras are much better at understanding which things are, even if they are worse at knowing exactly where things are in the 3D. The paper also include detailed robust analysis, and the results are very revealing. For weather, in rain conditions, LiDAR performance drops significantly because rain creates noise in the point cloud. BEVFusion improved detection by 10.7 over LiDAR only in the rain because camera features are more robust to precipitation. For lighting, at nighttime, cameras struck observably, but the camera only BEVFusion model dropped a lot. However, the multi-model BEVFusion achieved a 2.8 improvement for night mesh segmentation. This is actually a larger improvement than in daytime. Why? Because at night, LiDAR provides the geometric structure that camera cannot see, while cameras still contribute some useful information from red light and street light. For distance, BEVFusion show a 7.3 improvement for objects beyond 30 meters. This makes sense. LiDAR points become very sparse at long range, so the dense camera feature become increasingly valuable for detecting distant objects. The key takeaway here is that BEVFusion improvements are larger exactly where perception is hardest, bad weather, darkness, and long range. It is where true sensor fusion matter most. Now let me discuss the limitation I identify in this work. First, depth estimation accuracy. The entire camera to BEV pipeline depends on predicting accurate depth for each camera pixel. If the depth prediction is wrong, camera feature end up in the wrong BEV grid cell, creating misalignment with LiDAR feature. The authors acknowledge this limitation and said they leave depth supervision using ground truth depth for future work. I think this is a significant weakness because depth estimation is monocular image is an inherently difficult problem. Second, now critical analysis and insights. Now for my critical analysis, let's go behind, just summarize the paper. My first critique is about the BEV representation itself. BEV assumes a flat ground plane. it flattens everything along the head axis. This works well for standard driving on flat highway and urban road, but consider a multi-level parking, garage, highway, overpass, or hilly terrain. In this scenario, objects at different heights get collapsed into the same BEV cell, which causes confusion. My second critique is that the paper does not compare against 3D occupancy grid approach. Instead of flattening to BEV, you could keep the full 3D void representation. The paper shows BEV is efficient, but it does not improve better than 3D occupancy grid for perception. Maybe BEV is just the most computationally convenient choice, not the best one. Now for my proposed improvements, I suggest extending BEVFusion with temporal fusion. The idea is to take BEV feature from previous frame, align them to the current frame using ego motion compensation, since we know how far the car has moved, and aggregate them with the current BEV future. Before I conclude, I want to connect this paper back to what we have studied in class. The sensor discussion connects directly to the chapter 10 and 11 on sensor. We learn about camera versus LiDAR trade-off, and BEVFusion is a concrete example of why complementary sensor outperform any single sensor. The fusion approach connects to Professor Lee's slides on fusion in section 6.3. In the lecture, we study different fusion camera, element-wide project concatenation, and so on. BEVFusion proposes a fundamental different approach by doing fusion in a shared BEV space rather than the point level. Conclusion. To wrap up, BEVFusion makes 3 key points that I think are worth remembering. First, it challenged the dominant paradigm. For the 3 years before this paper, everyone was doing point-level fusion painting camera feature onto LiDAR point. BEVFusion showed there is a better way. Fuse in the shared BEV space that not sacrifice information for other sensor. Second, the engineering matter as much as the idea. The concept of BEVFusion will have been useless without the 40 times speed up in BEV pooling. The third, this is what I found most elegant about the paper. The insight is simple. Do not force one sensor into other space. Find a shared space that works for both. This same idea led to state-of-art results across mutators and benchmark with lower computation costs. Thank you for listening. I'm happy to take. Thank you. Here is the reference. Thank you.